Saxon Algebra 2, Lesson 35. 3 parts, you guys, 3 parts. You're getting into like the MLB here because no more of these lessons that are done in 10 minutes. We're grinding through. All right, angles and polygons is our first topic. Polygons are objects with straight closed sides, right? And one of our favorite polygons is the triangle, and we always know that the interior angles of a triangle will add up to 180, right? That's the interior angles. That's what we're talking about first. Interior angles of a triangle equal 180 degrees. Always. There are no exceptions to that rule. So sometimes we want to know how many angles are in the, what's the sum of the interior angles of a different object? Well, here's what's cool. If you just divide it into triangles, you can easily figure it out. Right? If it has 4 sides, rectangle, square, rhombus, what have you, then that's going to be 180 plus 180 or 360 degrees. If it has 5, just go here and divide it into triangles. There's 3 of them. 1, 2, 3. So that would be what? 540, right? 5 sides equals 540. So if you want to create a little formula to help you figure this out, you take the number of sides and you subtract 2, and then you multiply that number times 180. That's a little formula that will allow you to figure it out. That will tell you the sum of the interior angles. I'm writing that in there so that you can see. It says number of sides minus 2 times 180. So like in this example, it would be 4 minus 2. So that's 2 times 180, 360. This helps if John asks you a ridiculous question like, it's a 17-sided object. What's the sum of the interior angles? That way you don't have to try and draw a 17-sided object. But this, just drawing the picture will help you remember. Now, what about external angles? Well, we don't really talk about those very much. Exterior. All right. Whereas the interior angles require this little formula to figure it out, and it changes based on how many sides. The exterior angles of any polygon are exactly 360 degrees. And here's how you can prove it. Let's draw. They have to be concave, so I can't cheat, or convex, I can't cheat and do that. But so ignore that part. But here's our little self, and let's say we're starting right here, and we're gonna walk around and we're gonna count up all of these exterior angles, and you measure them by extending a line like that. They look really wonky. But you go around in one direction and you extend all the lines like that, okay? If you go around and you add up all of those, look what you've done. You've walked in a full circle. And the full circle has 360 degrees. So the exterior angles of any polygon is always 360. So let's see how we might use that in a problem. Both of these facts. Okay? Oh, I should include this. All right, you might want to pause me and make sure you have those in your book cover. I'm so excited. I just want to get to the problems. Example 35.1. All right. I'm going to show you in the book. It says find x and y. And what we have is this relatively complicated looking picture of all these exterior angles going around. And then there's a y that's an interior angle. All right, so we're going to use the trick that I've told you before. Go alphabetical. If you're not sure which one to try first, let's go alphabetical. And what we're going to do is we're going to try and solve for x. X is in two places. Both of them are on exterior angles. Y is an interior angle. So what we know is that if we added up all of these exteriors, they should equal 360. So I'm going to write them down. There's 65, 50. I'll show you where I'm getting these in just a second. 40, 80. Then there's x plus 55, and then there's x. I don't like the way I wrote that. Well, I'll leave it for now. The 55 I wish was lined up with this column, and I wish the x's were over, but you know what? I'm just going to cope. All of this should add up and equal 360 degrees. Okay, so what I did was I started here at 65, 50, 40, 80, x plus 55, and x. Y is an interior angle. It's not included. Okay? So now I am ready to adjust my light, and then I'm going to add, okay, 5 plus that 5 is 10, carry the 1, there's a 10, that makes 16, and then 8 more is 24, 29. So the numbers all add up to 290, plus I have 2 x's. So 2x plus 290 equals 60. These are all the exterior angles, right? And so now I just algebra the heck out of this. 2x equals 70. So x equals 35. Make sense? Again, that is partly an algebraic answer because right here, this angle, you have to add in order to get the actual degrees. Here, this angle would just be 35 degrees. There, the angle is equal to the algebra answer. But here we have to add to it. And this is the part that we're interested in. I'm just going to redraw this part in my book. It looks like this, and then it says y degrees, and then it says x plus 55 quantity degrees. We're supposed to find y. Now y is an interior angle, right, because it goes on to close off. This is an exterior angle, but look. These two meet in what is apparently, well, no, not necessarily that, but it is a straight angle. So these two together look like they need to be 180. So I'm going to say y plus, and now I can fill in a value for this, right? 35 plus 55 equals 90 degrees, as I suspected. So y plus 90 equals 180. That's really easy. So I get that y equals 90. And that is the actual degree measurement. So I can put that on there. And that's correct. Those are both correct. Yay! Okay, so that is how we can build some fun little problems with this exterior angle business that we've talked about. Change in topic. B, inscribed quadrilaterals. Oh, doesn't that sound so fancy? Here's what an inscribed quadrilateral is. We have a circle, and we have a four-sided object that sits inside the circle. The corners or vertices of the quadrilateral touch exactly on the circle. And so they have some interesting relationships. If a quadrilateral is inscribed in a circle, the sum of the measures of every pair of angles is 180. So let me show you what I mean by that. That means that angle A plus angle B opposite angles. And now I can prove it to you. Here, this is what you need to remember. Now you remember that when we have an inscribed angle, I'm going to draw it up here so I don't have to, no I'm not. I'm going to use my book, my bonus paper. Okay, inscribed angles, not inscribed quadrilaterals. These guys, right? We've talked about these. We know that if we want to call this x, this, the intercepted arc, will be 2 times that, right? So if we know this angle, we can multiply it by 2 to get this inscribed arc. If we know this arc, we can divide it by 2 to get the angle, right? That's super helpful. So, goodbye Ninja Man. If we think of angle A as an inscribed angle, then we know its intercepted arc is that, right? Because there's where A comes out like that, and then all of that is its intercepted arc. So this is 2 times that. But what about angle C? It's got to be the opposite angle, right? Look at angle C. Its intercepted arc is the other part of the circle. Not necessarily half, precisely, but between these 2 opposite angles, they eat the entire circle. If we take the amount of the intercepted arc and divide by 2, we get the angles. So if we take the intercepted arc of 360, then so the sum of the angles the sum of the angles, the 2 of them together, because we're talking about the whole thing, that has to be half of that, 180. Okay? So that's how we can prove that this is true, is by looking at the diagram and going, oh yeah, between the 2 opposite angles, they eat the entire circle. That's 360. So the 2 of them together must add up to 180. Super, super helpful. Let's do a problem that involves it. You wanna? I do. I think it's gonna be super fun. There's only one problem of this style too. Example 35.2, we're supposed to find x, y, and z. Here's the pick. Here's our little inscribed quadrilateral. They don't have to be squares or rectangles or anything remotely perfect. They can be wonky as can be. This is what John tells us. That's 80 degrees. That's 75 degrees. This is X degrees. That's Y degrees. 50 and Z degrees. Now, John's not super clear in this notation, but when we see this out here, that tells us that's the measure of the intercepted arc between whatever the two closest points are. So I can see, okay, Z's floating here, so it's between those two. The diagrams are a little nebulous at first, kind of hard to understand. And then 50 is the same way. 50 relates to the intercepted arc between the next 2 points. So that would be this part. I'll make it a little darker so we can distinguish. Okay, so that's how you need to interpret these floaty bits of information. All right, so we're supposed to find X, Y, and Z. Let's start with X. Okay, we can see that X has a buddy over here, right? An opposite pair. We know that X plus its opposite have to add up to 180, right? Because together they bite the whole circle. So X equals 100. And that's correct. Yay. So far, so good. How about Y? Okay, Y's buddy is 75, so we can do the same thing with him. Y plus 75 equals 180. Algebra, Y equals 105, also correct. Z, all right, let's look at Z. What can we find about Z? It would be nice if there was an angle that hit the circle here and here, but that doesn't quite work, does it? This one touches up here, but it intercepts over here. So the intercepted, oh wait, the intercepted arc is bigger than Z, but look. This angle intercepts this arc. So we know that Z plus 50, this whole big thing here, must be equal to 80, this angle that bites it, times 2, right? Because we double up the angle size to get the intercepted arc. So do you see how we can look and play around? Let me use another color to help. We look and play around with what we've got and how we might use it. And we can see that, oh, if we include both pieces of this arc, then it fits with this angle here. All right? Another good rule of thumb is that you usually end up using all the information John gives you. So at this point in the problem, we can go, what's up with that 50 degrees? How can we use that? But the intercepted arc is equal to twice that angle. So now we just do algebra. Let's subtract 50. Oh, this would be 160, right? And we'll subtract 50, and we get Z equals 110. And guess what? Spoilers, I looked ahead. That's the right answer. All right, beautiful. Part C is something new and something that's going to make you feel so dang smart. Are you ready? It's called fractional exponents. I don't think we've done these before. Maybe we did them at the end of last year, but I don't think so. I feel like it's new. If we want to use symbols to write the square root of 2, this is the way we've done it up until now, right? We put it in a little pig house and it's cute. But there's another way that in sometimes is preferable. Weird, right? This is the same thing as saying square root. What if we want to take the cube root, I made it one word, it's not, of, let's say, 27. That's what we want to take. We've always done it like this, right? We put a little 3 there, right? But another way we can write it is 27 to the 1/3. So the number in the denominator reflects the root that we're trying to take, right? Here we want a square root, here we want a cube root. The number on top, we just put a 1 there. We'll get fancy with that later, but not yet. Oh, we will later in these examples, all right? So for now, we're just talking about the denominator here. So let's take a look at how we would simplify some of these. Ready? Look, I got so hardcore on that problem, I burned through my page. That's when you know I'm really having a good time. Okay, 4 to the -1/2. Okay, and what we're gonna do is we're gonna work these problems without resorting to pig houses. We're not gonna use that symbol, we're just gonna simplify based on this. But the first thing we notice is this negative exponent. As we know, that's different than a minus sign. That is a trapeze. I wonder if I'm spelling trapeze right. Somehow it looks weird to me. So the first thing that we do is we flip that boy down and handle it that way, all right? Now, we need to simplify this part, and we say, what is the square root of 4? Oh, well, that's 2. So our final answer is 1/2. I enjoyed that, didn't you? Easy, fun, makes you feel smart, right? Example 35.4. Say yes, it should make you feel smart. Okay, here comes another one. -27 to the -1/3. Ay, ay, ay. We cover this one up. We're going to deal with that last. We address this one first. We always deal with those negative exponents first. So now we're going to write this as 1/27 to the 1/3. But I still have my finger over it, so that's just everything else. Now we know that we're saying here, what is the third root or the cube root of 27? Oh, we know that's 3. I did not choose that example on purpose before, but it sure worked out perfectly, didn't it? And we've got our answer, and now we take that off and add the minus sign back in. Okay, so I did a refresher for the Algebra 1 kids on this situation. This we call a minus sign. And you know how to handle it. It means take the opposite. It means you cover it up if you can, if it's unprotected. But this is only a trapeze. It's not a negative sign in the way that this is. It doesn't behave the same way at all. All this is an indicator that we should take the reciprocal of this base and exponent. And once we flip it, it burns off and it goes away. I wish this was a different symbol because they often get confused, but they mean very different things. So that's why I call this a trapeze, is because I don't even want to think of that as a negative 1/3 because that just muddies the water. Okay, now we're going to up our game. 16. What did I do? I put a number besides 1 up there. There's 2 ways to interpret this. One way is to say we're going to take 16 and we're going to find the square root of that, and then we're going to cube it. And see how, remember with our rules for exponents, if you have a number that you're raising to another number, a power to another power, then you multiply those, right? So if I multiply 3 times 1/2, I get that back again, don't I? So I did it right. But the other way we could do it is to say 16 to the 3rd and then take the square root of that. Now, you guys know my general theory. Both of these would be right. This multiplies back to 3/2. So this is the way we break down a problem that has a number besides 1 in the top and bottom. I say make our numbers smaller before we make them bigger. So that tells me this is by far the preferred method. I'd rather take the root first and then blow it up than I would take this number, blow it up to 16 to the third power. That's gonna be a pretty big number. And then try to find the square root of it? No, this gives me a headache because that's gonna make such a big number. So I always wanna take the root first and then power it up. So I'm not gonna go this path. I'm gonna go this path. 16, the square root of that is 4. 4 cubed equals 4 times 4 is 16 times 4, that's 64, isn't it? Yes. Okay, so either way will work, but this number I see John mentions in here, if you take 16 to the third power, it's 4,096. What? No, that's crazy. We don't want to do that. So we make our numbers smaller before we make them bigger. And we have one more. I think this is the last problem. Yes. I'll squeeze it in down here. 35.6. It's minus 8 to the minus 2/3. Oh, Lord have mercy. I'm going to use all this space. Okay. Always we deal with the trapeze first. That is not a minus sign, that is a trapeze. I am going to make this 1 over minus 8 to the 2/3. I'm going to cover up that minus sign. And then I'm going to remember that I can deal with this 8 two ways. I can make it 8 to the 1/3 squared, or I can make it 8 squared to the 1/3. I would always rather do it this way. I want to make the number smaller before I make it bigger. Remember, the fractional part makes it smaller and that number makes it bigger. So what is 8 to the 1/3? What is the cube root of 8? It's 2, right? 2 times 2 times 2 equals 8. So this much, then this becomes 2 squared. And so 2 squared is 4. Now I've dealt with all of that, and the only thing left is the minus sign. So I add it back on at the very end. That is my final answer. And if you can make sense of this, even if you couldn't reproduce it right this second, but you can follow along with what I'm saying, whew, you are rocking this. Absolutely amazing, okay? This is hard, this is complicated stuff. So that is lesson 35. Lesson 36 is one that I know we've done before and I know you like it. So look forward to that. Bye.